Hi guys, so this week we are moving away from our traditional polygons that we had been working with. We were working with quadrilaterals, we were working with parallelograms. Now we are moving into circles. So there are quite a few vocab terms we have to learn in this section and quite a few different problems we have in this section. So first thing first, we're going to start with our vocab terms here. So if I'm talking about the chord in a in a circle, I'm saying a chord is just a line whose endpoints are sitting on the circle itself. So it's not passing through the center. It's just a segment that the endpoints are sitting on the circle. The diameter is very, very similar to a chord. The endpoints are still sitting on the circle, except it goes through your center point. It contains that center point. And the radius is just half of the diameter. It's connecting your center point with just one endpoint sitting on your circle. A secant is similar to a chord, except a chord had endpoints, whereas a secant is a line that'll go through it. It'll keep continuing on. And a tangent is also similar to that, except a tangent is going to hit a point on your circle once, and that's it. It's not going to cross through it. It's just going to hit it once and keep continuing on. So a tangent only has one point of intersection. So there's a lot of questions in this chapter, in this section, asking about common tangents. So a common tangent, you have to have more than one circle. A common tangent is drawing a line that hits both circles, and on both circles that only intersects that circle once. So if we have two circles like this, they're separate, they're not touching at all, I can draw a tangent like this. So it hits this circle once, and it hits that circle once. So that's one tangent. I can also draw a tangent like this, where I'm hitting this circle once, I'm hitting this circle once. So now I have two tangents. I can also, let me twist my paper. I can also draw that line right on the top where it's intersecting the circles once. And I can also draw a line on the bottom here where it's intersecting once. All right, and there's no other lines that I can draw here where the lines are going to hit each circle just once. Okay, anything else I drew wouldn't end up being a tangent. So there are four, I'm going to abbreviate, there are four common tangents in this type of problem. In the next problem, we see our diagram's a little bit different. Right now our circles are touching. So I can't do those like two tangents in the middle, right, where I had an X. I can't do that anymore. My tangent in the middle is just a straight line where it's going to just hit that once. Okay, and then I can still do, pretend that hits it. I can still do this one on the top, and I can also do this one on the bottom. So that stays the same. So in this one, right, there's going to be three common tangents. Okay, in any diagram that are similar to these, where there's two separate circles, they'll always have four common tangents. If the circles are just touching at that one point, there will always be three common tangents, and the same will go for the bottom figures as well here. So on this bottom one, we have two circles intersecting. I can't draw that middle line like I did up here, because if I did that, I would be hitting both circles two times. So that one goes away. The only ones I have left are the ones on the top and the ones on the bottom, where I'm hitting each circle just once here. So these types of diagrams would only have two common tangents. On a diagram where I have a circle and then another circle within it where it's touching just the edge of that outer circle, I can draw just this one tangent here. And that's going to end up hitting right at the point of intersection where this little circle is intersecting with this larger circle here. So there's only one common tangent here. And when I have a diagram like this, right, kind of looks like a donut, I have a small circle inside of the larger circle, and they're not touching anywhere, right? I can't draw a line that's only going to touch this circle once and only this circle once. Okay, I can't draw anything if I try to do this, right? Then I'm going to hit this outer circle twice. If I drew something like this, I would hit the inner circle twice, right? So there are no common tangents in these types of diagrams where they're a larger circle with a little circle inside without them touching. This type of diagram, they're called concentric circles if they share that same center point. But they will not end up having any common tangents. Our next type of problem is when we're given this type of diagram and it's asking us, are these triangles, the circle, is AB going to be tangent to this circle? And part of the notes in our rules, it says, in order for a line to be tangent, it has to form a right angle with that line with a radius, right? So if AB is tangent, right, I have to form a right angle here. And in order to check that, right, I can see I have a right triangle, right? It goes back to the Pythagorean theorem. So we're still pulling in information we learned about triangles, even though we're now working with circles. So we try the Pythagorean theorem. We say 9 squared plus 12 squared, is that going to equal 15 squared? Okay, 9 squared is 81, 12 squared is 144, and 15 squared will get 225. So we want to know, is that going to be equal? When we add these, we do end up getting that 225 is equal to 225. Since these are equal, right, we've learned that if our Pythagorean theorem works, we have a right triangle, right? And if I have a right triangle, right, that means that these lines are perpendicular. And our rule says if our tangent is perpendicular to a line that connects the tangent point to the center, then we have a tangent, then it works. So we are good here. It forms a right angle. We were able to tell it forms a right angle by performing our Pythagorean theorem. We also want to check this one as well, right? We also want to know, is AB going to be a tangent here as well? So if we do that, right? Oops. If we do that, we would have 12 squared plus 14 squared. We want to know, is that equal to 17 squared? So we would have 144 plus 196. Is that going to be equal to 298? Okay, and when I add these, when I add the 144 and the 196, right, I get 340 equals 289. Okay, so in this case, our Pythagorean theorem didn't end up working out, right? 340 does not equal 289, which means this can't be a right triangle. Since it's not a right triangle, I don't have a right angle formed here, which means AB is not going to be a tangent. It would have to be perpendicular. And because we just proved that this is not a right triangle, that means there's no right angle for these to be perpendicular. So that does not work. Okay. So this is the first part of this section, learning about the different vocab of the different lines and segments of circles, being able to identify and draw tangents and know where they are, and then being able to tell if a line is in fact a tangent when you're given a triangle here. That was the first part of this section. The second part of this section is something like this. So we have the fact that AB is a tangent. We know that. So it means it forms a right angle. So we know we have that right angle. We need to figure out what R is. We need to know what the radius is. So again, the radius is always the center connected to a point on the circle. So even though I drew two lines here, right? No matter what, I'm going from the center to a piece on the circle, or center to a point on the circle. These have to be equal. That's why they're both labeled R. So in order to figure out what R is, since we know this is a right triangle, we know that the Pythagorean theorem has to work on this. So we're going to use that fact again to solve what r is going to be. So, right, if I wanted to solve my Pythagorean theorem, r and 8 are my legs on this triangle. So I would say r squared plus 8 squared, and that has to equal our hypotenuse squared. In this case, 5 is just referring to this little segment on the hypotenuse, and r is only referring to this little segment on the hypotenuse. If I want to refer to the entire hypotenuse, I would have to call this entire hypotenuse r plus 5, right? If I knew r was, say, 7, right, we would say 7 plus 5 to get 12, right? That would represent our entire hypotenuse. So we're saying r plus 5. So we need to take that, we're going to put that in parentheses. We also have to square that as well. So when we do this, we have r squared, right? 8 squared gives me 64. And when I square this, right, remember if I ever square anything, we're really doing r plus 5 times r plus 5. So if I distribute, I have r squared plus 5r, right, I'm going like this, I'm doing my FOIL method, plus 5r again, plus 25. And we can simplify that right side. We can say r squared plus 64 equals r squared plus 10r plus 25. And if I want to go through and I want to solve this, right, I can notice if I wanted to subtract the r squared on both sides, it ends up canceling out. I'm just left with 64 equals 10r plus 25. I can subtract the 25 on both sides. I'll end up with 39 equals 10r. It's not going to come out perfect when I divide by 10, but I'll get r is equal to 3.9, which is good enough, right? We can use our decimals. So we just used our Pythagorean theorem using all of these variables here. We were able to take our Pythagorean theorem, solve it out, and we were able to use that to find our radius. Okay, even though we only had 2 small pieces of information, we were able to figure out our radius, again, still using our Pythagorean theorem. So that was another important fact to remember. You'll come up with these problems on the assignments as well. And then the last type of problems you'll see are something like this. So we already know Kj and Mj are tangents. We want to know what is x. So the last piece of information, the last rule we found in our notes was saying if I have a common point outside my circle and I draw my 2 tangents to the circle, those 2 tangents have to be equal. So if I'm going to figure out what x is, I know that Kj and Mj, because they're both tangents and they both end at j, they both end at a common point, we can just set them equal to each other. So we'd say 5x plus 17 is equal to 12x plus 3, and we can just go through and solve, right? So I'm going to subtract the 5x from both sides. We would get 17 equals 7x plus 3. We can subtract the 3. We get 14 equals 7x. And when we divide, we get x is equal to 2. Okay, so again, that was the last rule of this section, was saying if you have a common point and you draw the tangents to the circle, those tangents have to be equal. So there was a lot of information in this section all about the circles. Like I said, it was a lot of vocab at first to get used to, and then using the definitions of that vocab to then solve different problems. And again, you can notice on these types of problems, on this type of problem, the Pythagorean theorem, right, our triangle geometry isn't really going away. We're still pulling that in to this section. So like I said, this covers all types of problems that you will come upon in your assignment. So make sure you can go back and use this video as a reference as you're doing them. And also, if you guys have any questions, you know, always to give me a quick email and ask away.